Hello and welcome to another segment of Geology 1 Processes and Products Lab DVD. Today our topics will be sedimentary rocks and sedimentary structures. Before we can start with any sedimentary rock topic though, we have to review a few concepts of weathering. Okay, if we go to the PowerPoint slide, we see that weathering comes in two varieties. We can have physical weathering, which is also called mechanical weathering. And in physical weathering, what we're doing is a process known as disintegration. We are taking something that's large and breaking it down into smaller pieces. It simply results in smaller fragments, much as taking a big rock and taking a hammer and hitting the rock with a hammer will result in smaller pieces of the original parent rock. Now, the pieces are smaller, but size is the only thing that's different. The chemical composition is still the same. However, if you look at chemical weathering, you note that this is decomposition. So, not only do we end up with smaller pieces, but we also end up with smaller pieces of a different composition. We have chemical weathering whenever usually water or oxygen in the air will chemically react with some of the minerals in the rock and change their composition. So, physical weathering results in smaller pieces but the same material, and chemical weathering results in smaller pieces but it's different than the original material we started with. Well, how does that relate to sedimentary rocks? When we look at the formation of sedimentary rocks, the most common type of rock on the Earth's surface, we're looking at formation from pre-existing rock types. So we can have sedimentary, igneous, or metamorphic rocks all contributing either smaller pieces of rock or ions in solution to make a new rock known as a sedimentary rock. The process of sedimentary rock formation is lithification, and that involves the compaction and cementation of these pre-existing rock pieces, fragments, or clasts. We have a couple of different types of sedimentary rocks as well. We have clastic or detrital sedimentary rocks, and we can have chemical sedimentary rocks such as evaporites, inorganic, or if an organism was involved, we would have a biochemical sedimentary rock. Now remember, when we classify any type of rock, we look at two things, right? We look at the texture and we look at the composition. So let's start off with the texture. Not as an evaporite, but as pre-existing pieces or clasts of other rocks that have been transported, deposited, and over time lithified together. When we look at these clasts, we also want to look at the size, shape, and sorting of the clasts. Crystalline rocks won't be classified according to the size, shape of the particle. They're simply going to be evaporation of water leaving behind the minerals. Now, in a clastic texture, we look at the shape of the individual clasts and the sorting. Now, please take note, the shape does not mean the shape of the rock. The shape of the rock may be very round or very angular, but what you're looking for to classify according to a clastic or detrital sedimentary texture is the shape of the particles or clasts within the rock. We can have rounded or angular fragments. The sorting describes how well the different clasts fit in with each other. It's either well sorted or not so well sorted. I have a couple of diagrams, some photos to show you. In this, we see some clasts that are very well rounded. Note that all the edges are missing from these individual little pebbles. In this middle diagram, this middle photograph, we see that it's rounded, but on the other hand, some of the angles are still sort of preserved as rounded angles. However, this shows very angular quartz grains. No weathering, rounding whatsoever. Remember, when you weather, because you have more surface area exposed at a corner or a point, that tends to weather first. So when you see very angular grains, this tends to imply that it wasn't weathered very much and it wasn't transported very far, at least not by running water. Sorting, on the other hand, describes just how well individual clasts fit in with other clasts in the rock. This is very well sorted. They're all about the same size and the same degree of roundedness. In the middle picture, you see moderately sorted. Some of them are larger and some are a little bit smaller. However, compare that to poorly sorted. Here we have some very angular grains. This one looks like it's a little rounded, very small and very large pieces. So sorting can describe the class of a sedimentary rock as well as the type of shape it has, whether it's rounded, well-rounded, or angular. If we classify sedimentary rocks according to the classed size, we start out with larger class and work our way down. Here we see in clastic sedimentary rocks, we have a gravel-sized class. These are the bigger ones. The sand size, this would form sandstones. The silt size, and this is a siltstone. And finally, the smallest particle, the clay size, or the shale. Now, in the gravel size, we can have two different varieties of sedimentary rocks that are produced. If we have very well-rounded clasts, we end up with a type of rock known as a conglomerate. If, however, we're looking at angular clasts, we end up with a rock known as a breccia. Sand has a different connotation in geology in a couple of different situations. Sand can be commonly used to describe quartz sand, but sand is also a size category as well. So keep that in mind when you're classifying sedimentary rocks. These photos show some of the different varieties of sedimentary rocks. This one's in the field, and I wish we had a scale here to show you. This is a conglomerate. There are nice pebble sizes that have been cemented together, compacted and cemented, lithified to form this conglomerate. Now over here in this corner you see some pretty large size clasts, but they're not well rounded. They're angular. So although we're looking at about the same size of the clasts, because these are angular, this would form a rock known as a breccia. Here we have sand-sized particles that have been compacted and cemented to form a sandstone. And finally over here, you can't even see the individual particles. They're too small. They're clay size. This would be forming a shale. I do have a couple of rocks to show you. We'll move them over here. Okay. You can see, with my hand for scale and also a pen, put that right here, you can see that the individual clasts of this rock are fairly large. And since they are rounded, not all of them well rounded, this would be a conglomerate. The smaller one in front, show this little guy, he's also, or she's also, a conglomerate as well. Now, what if these individual clasts were angular? Let's put these two together. Let's see if I can get that. There we go. Okay, notice how these are fairly angular clasts. This would be a breccia. This, on the other hand, look, rounded conglomerate. So we're looking at big pieces in both of the rock types, but in one instance, if it's rounded, we have a conglomerate over here. And if it's angular, we have a breccia. Let's move down the size scale. This is an example of a sandstone. There are some individual sand-sized grains that have been deposited, compacted, and cemented together. Now, again, we don't always have to have quartz sand making up a sandstone. We can have feldspars, and I have a sample here. If you could examine this rock up close and personal, you would see that the individual grains are not quartz grains. They are grains of feldspar. In this case, although we have a sandstone size, we have a special name for this little rock, and we call this an arkose, A-R-K-O-S-E. And the arkose describes the composition as well as the size, sand-sized, but feldspar. Let's move down a little bit in size. And here we have a siltstone. That's a siltstone. And this is a shale. This would be very, very hard to see the individual little pieces without getting it under a microscope. Clay-sized particles make a shale. Silt-sized particles make a siltstone. Now, commonly in some geology texts you will see both size particles referred to as mud or mudstone. If you are forced to make the distinction between a siltstone and a shale, there is an easy test. And it again involves putting a rock in your mouth, so you may not be agreeable to that. A siltstone, if you actually try to bite it, it feels gritty against your teeth. You can still distinguish those individual silt-sized particles with your teeth. A shale, on the other hand, you can't. So an easy test between a siltstone or a shale, when no one's looking, is to put the siltstone or the shale in your mouth. And if you can still feel that individual grit, you have a siltstone. Okay, now when we describe sedimentary rocks, again, we have to look at texture and composition. We've just covered what we look at as far as texture. We can have clastic texture, and we divide those sedimentary rocks into groups based on the size of the individual particles. We just looked at the conglomerate or breccia, the sandstone, the siltstone, and the shale. Now, what happens if we have sedimentary rocks that are formed not from pieces but by evaporating bodies of water? We can have a special type of sedimentary rock with a crystalline structure known as an evaporite. This is inorganic, meaning that it formed not from a living animal, not from an organism. On the other hand, we can also have chemical sedimentary rocks that are formed by organisms. Pieces of shells, for example. These are biochemical sedimentary rocks. I have a couple of photographs to show you. In this one, I have rock salt or halite. This would be an inorganic sedimentary rock. This would be an evaporite. This guy up here, gypsum, the stuff that you use in sheetrock, is also an inorganic sedimentary rock. Here we have chert, which is made of silicon dioxide. Here we have also, this can be an inorganic evaporite sedimentary rock. Now here we have a piece of coal. Coal is made from the remains of plants and animals, so it is organic in nature. Would coal classify as a mineral? No. Remember, minerals have to be inorganic as well as solid and crystalline. Now this photograph shows a salt flat. It is an ephemeral lake, meaning that it fills up with water when the rainy season comes, but then the water evaporates away and leaves behind the minerals that have been carried to the lake bed. These would be inorganic evaporites. And I do have a couple to show you. Okay, over here we have, this is rock salt, formed from the mineral halite. What's an easy test for rock salt? That's right, taste it. It tastes salty. Now this one, we've seen a lot of these. This is soft, remember on the Mohs scale. We can scratch it with the fingernail. The fingernail is 2.5. This is less. It has a hardness of 2. This is gypsum. It is an inorganic sedimentary rock. It's crystalline. It's an evaporite. Now the last one over here is limestone. This piece happens to be inorganic. Limestone comes in a couple of varieties, and we'll look at a few more in just a minute. Limestone can form inorganically. Now what's an easy way to test for limestone? You may know that limestone is formed of the mineral calcite. And we have an easy test for calcite. We drop dilute hydrochloric acid on it, and it will fizz. Let's see if we can get a fizz going here. There we go. This is limestone, sedimentary rock. Now, I have a photograph of the White Cliffs of Dover in the UK. And these cliffs, as they're called, are made of a white chalk. Now, What made this white chalk? Over time, the remains of very tiny microscopic animals were deposited, and you can imagine the number of organisms as well as the amount of time involved. This slide shows what the coccoliths look like underneath a microscope. So let's go back to this one. This rock is composed of these microorganisms. So this would be a biochemical sedimentary rock. We can also see other varieties of limestones, fossiliferous limestone that includes fossils. We have something called coquina as well. This is cemented pieces of shells. Sometimes we have oolitic limestone where we have a small nucleus that slowly collects layer upon layer of calcite. This tends to form in warm tropical waters, and it forms much like pearls do, slowly adding layer upon layer to a little bitty nucleus. I do have some biochemical sedimentary rocks that I can show you. There we go. And you can see this is fossiliferous. It happens to be fossiliferous limestone. How would we tell if it's limestone? That's right, we drop a little bit of acid on it, and there we get a really nice fizz. Again, you don't have to use strong acid. 0.1 molar is just fine. Now, the one next to it is a coquina, and it is made of fragments of shells. Let me flip it over this way. I think you can get a better. There you go. Little bitty shells that have been cemented together. And again, they're made of calcite. How can we tell? Whoops. Drop a little bit of acid, and we see it effervesce. So, if you're given a set of sedimentary rocks in your lab rock kit, how do you identify which ones are which? Well, you start out very basically by identifying the sample as either biochemical. If you can see fossil pieces, you have a biochemical sedimentary rock. Or you can have an evaporite. These will be crystalline, but they won't have any shell pieces, or they won't have been made by an organism. They will be chemical evaporites. Or if you can see individual pieces, you have a detrital sedimentary rock. So you need to classify immediately whether you have biochemical or whether you have crystalline rocks, or whether or not it's made of pieces of rock. Now, the only one there that may throw you off with detrital is the shale, because it's very hard to see the clay-sized particles without magnification. However, shale's pretty distinctive. You won't see any type of crystalline structure, so therefore you should be able to pick out that shale. You need to identify the texture next, especially if you're looking at a detrital rock. What size are the particles? And go from there. And any special features of the sample. If it's quartz, you can say quartz sandstone if you have sand-sized particles. If you have feldspar in the sand-sized rock, you need to call it an arkose. Okay, let's look at some sedimentary structures. Sedimentary rocks are the most common rock type on the surface of the earth. So let's look at some of the structures that are associated with sedimentary rocks. Most commonly, we see layering or bedding, and these are bedding planes that separate layers of rock. I have a couple of samples here. Whoops. There we go. This you can see, this is actually cut in this direction. Well, let me try to get it. There we go. Originally, it's laid down as nice horizontal bedding planes, and we see some light and dark layers there. Now this guy, note that the bedding planes are at an angle. Now I'd like to say that this is cross bedding, but it's not. You can see down at the bottom here, we have an erosional surface. This would be an unconformity or an angular unconformity. It simply means that if we can tilt these rocks over, let's see, let me do this. They were originally laid down nice and horizontally, like this, and then over time the rock body was lifted, tilted, eroded We have an erosional surface here right at the top. You can see it. And we've since deposited other rock layers on top. That's also an example of bedding. Here's a photograph that shows pretty much what we saw in this individual sample. We see the layering coming through here, and we also see layering at the top. These weren't formed at an angle. Instead, they were laid down flat, and something tectonically happened, uplift, erosion along this surface, and then probably submersion again, and we had new layers deposited. Okay, cross beds are beds that are deposited at an angle to the surface. We can see this in a desert environment, aeolian deposited layers, wind deposited layers, as well as some layering in river systems. We tend to have, at a delta, we get top set, fore set, and bottom set beds. So it kind of looks like we have a little bit of cross bedding going on. With a graded bedding is an upward decrease in the grain size. Well, what does that mean? It means that we have the larger pieces on the bottom and the smaller pieces on the top. Basically, if you go down to a creek or a river and scoop up some sediment, shake it up with some water, and put your glass down, you will notice over time that you have the bigger pieces fall out right away, the sand-sized pieces. But then, as you leave it for a while, you see some particles floating down in your water. After you wait a little bit longer, maybe 2 or 3 days, that cloudy water may get clearer as the clay-sized particles filter down. So graded bedding just means the bigger particles are deposited first, and then the finer sized stuff. I do have a rock. I can almost see this. Let's stick this here. There we go. Let's see, do I have that upside down? No, here we go. Look at, in this little bed, we have some pretty big size particles here, and look how we have smaller size as we move up. I have a little disturbance over on this side. But we have bigger moving up into smaller. This would be an example of a graded bedding system. Now, graded bedding most commonly occurs in the deep marine environment, formed through something called turbidity currents, or underwater sediment flows. Here you see in this diagram, we're looking underwater, and let's see, we're up here. This would be our land surface, and here is the continental shelf, and then the shelf slope break. This becomes very unstable and moves rapidly downhill because of gravity. And as this sediment water flow stops moving, hits a nice flat area, you'll see the bigger particles settling out first, then the medium size, and then the fine grain size. This would be graded bedding. Bigger at the bottom, finer at the top. Other sedimentary structures include ripple marks and mud cracks, anything that can be formed in nature and preserved in the rock. And here are a couple of neat photos taken out in the field. You can see in the top photograph, these are ripple marks, but they are stone. Note we've actually even drawn a line when we were out in the field with an arrow showing the direction of the current way back in Paleo times. This is the same environment modern day, and you can see how well these ripple marks have been preserved in the rock. Other than ripple marks and mud cracks, we can also have secondary sedimentary structures, concretions, or easily removed masses from the rock. In other words, we have a cavity or a void, and after the rock is formed, we end up getting deposition of minerals within the spaces, concretions. Here are some examples of concretions that were collected in Mississippi. They easily separate from the rock or soil, the weathered soil in which they were formed. But they are secondary structures, meaning that they were not formed originally with the sedimentary rock. Now, one of my favorite secondary sedimentary structures would be that of a geode. Geodes, we have a cavity in the rock, and minerals are precipitated from the solution into the cavity. So therefore, the minerals have time to grow, and we have a couple of examples there. Here is a partial geode. There we go. Quartz crystals. Now originally this was a big mass, and I only have about a third of it preserved. But these crystals had an open space within which to grow. Now what does a geode look like before you cut it open? Well, I have another example to show you. And this looks like a regular old pebble until you cut it open with a rock saw, and inside you can see nice little crystals that have grown into that void space. These are geodes. Okay, the last thing that we're going to mention about sedimentary rocks is the existence of fossils in sedimentary rocks. You find fossils in sedimentary rocks with very few exceptions. This is a photograph of a trilobite. Trilobites are great index fossils because they were only alive during the Paleozoic era. So all trilobites have to be at least 245 million years old in the fossil form. I have an example to show you as well. This is one collected out in the field. It's not as fancy as the trilobites, but you can see, especially on the top surface, that we have lots of individual gastropod shells within this matrix. So this is a fossiliferous rock. The sedimentary rock has preserved the remains and traces of past life. Well, that will conclude our talk today on sedimentary rocks and sedimentary structures. As always, if you have any questions, please feel free to email your instructor. He or she will be happy to help you. Thank you very much for joining me today. Have a good day.